So, last time we defined what a Dedekind domain is. Let me recall the definition for you. A Dedekind domain is an integral domain which is Noetherian, integrally closed in its quotient field, and every non-zero prime ideal is a maximal ideal. We proved that a principal ideal domain is a Dedekind domain. We defined what a fractional ideal in a Dedekind domain is. So, a fractional ideal of a Dedekind domain is a submodule of its quotient field, which is finitely generated as an R module. Okay. And we proved that A is a fractional ideal if and only if there exists a non-zero x such that A times x is actually an ideal in R. Okay. And this time we are going to start with the proof of this main theorem about Dedekind domains. It says that every non-zero fractional ideal in a Dedekind domain, actually let me state it slightly differently. So, it says that the set of non-zero fractional ideals in a Dedekind domain forms a group. Okay. So, if I give you a set and I tell you that it forms a group, your first question should be, what is the multiplication in this group? What is the binary operation in this group? Okay. So, what I am doing is I am taking two fractional ideals, I can multiply them. So, let me tell you what the multiplication is. So, group operation. So, if A and B are two fractional ideals, then A times B, this is set of all finite sums like this. So, I going from 1 to R for some R AI BI such that AI is in A and BI is in B. Okay. So, this is exactly how you define multiplication of two ideals in a ring, and here I just define it as multiplication of two fractional ideals. Okay. So, so here is an exercise for you. If A and B are fractional ideals, then A times B defined as above is also a fractional ideal. Okay. So, if A is a fractional ideal, B is a fractional ideal, their product is also a fractional ideal. So, although this is an exercise, let me just orally sketch a proof for you. So, what do you need to show? You need to show that it is a R submodule of K, and that is clear from the definition of how the product is defined, and you want to show that it is finitely generated over R. So, you are given that A and B are both finitely generated. So, you take product of their generators. So, if A has m generators and B has n generators, then you take their product, there will be m times n elements, and you can show that those m n elements generate A times B. Okay. So, that's the proof of this exercise. So, it is not hard, and especially after I have done the sketched the proof for you. Okay. So, what we want to do is so we have now defined a binary operation on the set of non-zero fractional ideals, and we want to show that it is a group. So, what does it mean? What does a group have? Well, first of all, it has identity. Secondly, the group operation should be associative, and thirdly, every element should have inverse. Okay. So, so if you take the fractional ideal, take the fractional ideal R itself, right. R is also a fractional ideal. of R. Okay. Now, A times R is equal to A. This is very easy to check, right, because there is 1 inside R. Yeah. So, A times R contains A, and on the other hand, because A is an R module, R any element of R times an element of A is contained in A. So, hence R is identity for the group operation, for the operation defined above. Okay. So, we have identity in our set with the above binary operation. Okay. Associativity is easy. So, the multiplication in R and in QR is associative, and hence multiplication of fractional ideals is associative. So, the non-trivial point is to prove that every fractional ideal, every non-zero fractional ideal has an inverse. It is also clear that multiplication of fractional ideals is commutative. So, if we prove when we prove that this is a group, we will get that it is an abelian group. Okay. So, what it means if so what does this mean? If A is a fractional ideal, then there exists B, a fractional ideal such that A times B is equal to R, right. That is what it would mean, because R is our identity element with respect to this group operation, binary operation. Okay. So, we are first going to do this for prime ideals, and then we will do it for general fractional ideals. Okay. All right. So, how do we do that? Before doing that, let me prove a lemma for you. So, first let us prove the following lemma first. Okay, what does it say? It says that if R is a Noetherian ring, then any ideal in R, any non-zero ideal in R contains a finite product of prime ideals. Okay. So, if R is a Noetherian ring, so I am not even assuming that it is a Dedekind domain, then any non-zero ideal of R contains a finite product of prime ideals. Okay, let me write this more mathematically. So, if A contained in R is an ideal, is a non-zero ideal, then there exist prime ideals P1, again non-zero, sorry, P1 up to Pm, non-zero prime ideal. So, let me write non-zero here. I mean R could be a domain and you could just take 0 as the ideal, which is a prime ideal, such that P1 up to Pm is contained inside A. Okay, it need not be equal to A. So, this holds in Noetherian rings, not just in Dedekind domains. For Dedekind domains, we will prove an equality here, existence of an equality here. So, it's that result is more specific to Dedekind domains. Okay. All right. So, this is a very basic thing in commutative algebra. So, let us say that this does not hold for all non-zero ideals in A. So, let us say let S be the set of all non-zero ideals A of R such that there does not exist non-zero prime ideals P1 up to Pm with product of those things, those prime ideals contained in A. Okay, so, all I am saying is that let us say the lemma is false and then I take S to be the set of all such ideals. So, if S is non-empty, which means the lemma is false, then it should have a maximal element. Okay. So, if S is non-empty, then S has a maximal element because R is Noetherian, as R is Noetherian. Okay. So, let us say that this max, so what I mean is non-empty, okay, not non-zero. So, let A in S be a maximal element. So, this is the usual thing that one does for proving anything about Noetherian rings. So, you say that you take all the ideals that violate whatever you want to prove, and if that set is non-empty, it will have a maximal element, right, with respect to inclusion, and we take that maximal element and then we try to get a contradiction. Okay. All right. So, we know two things. Firstly, A cannot be a prime ideal. Because if A is a prime ideal, then of course, A is a prime product of prime that is contained in A, right. So, it cannot be a prime ideal, which means that there exist x and y in R such that x is not in A, y is not in A, but x y is in A, right. So, you have otherwise A would be a prime ideal, right. Okay. This means that if you take the ideal generated by A and x, this contains A but is not equal to A. Similarly, the ideal contained generated by A and y, it contains the ideal A but not is not equal to A, which means that A and x are not, this ideal is not in S, and similarly A and y is not in S, because if they were in S, that would contradict the maximality of A. Okay. So, there exists P1 up to Pm non-zero prime ideals such that the product is contained in A comma x, the ideal generated by A and x. Similarly, there exist Q1 up to Qn, again non-zero prime ideals such that their product Q1 up to Qn is contained in A times A comma y, right. So, I take their product P1 up to Pm, Q1 up to Qn, this will be contained in product of these two ideals. But this is contained in the ideal generated by A and x y, which is contained in the ideal A, right. So, this is a contradiction. Hence, S is empty and the condition holds for all ideals inside of a Noetherian ring. Okay. So, I am going to use this lemma for our Dedekind domain. Now, we go back to the proof of our theorem. Okay. So, we go back to proof of our theorem. So, first we prove that every non-zero prime ideal in R has an inverse. Okay. All right. So, how do we do this? Well, if you think about it a little bit, so let P be a non-zero prime ideal. Non-zero prime ideal. One way to try to construct inverse of P would be you take every element in P and take its inverse, right, and you take the R module generated by those inverses. The problem with that is that you do not know whether it is finitely generated or not. Well, you could just take the set of generators of P and then take their inverses, but that will not give you the right thing, because you can't write inverse of any element of P as a linear combination of inverses of generators. That need not be true in general. Okay. So, you go back, I mean essentially you do want inverses of all the elements and you want to prove that that is a finitely generated R module. So, a way to do that is define it as follows, which makes it easier to understand. So, what you do is you define P bar to be set of all elements x in K, remember K is the quotient field of R, such that x times P is contained in R. Okay. So, you do something slightly different than taking inverses of all the non-zero elements in P. Okay. And this it turns out that this gives you the right object, and we will show that. So, we will prove that P bar is equal to P bar P is equal to R, right. So, P bar will turn out to be the inverse of our prime ideal P. Okay. So, this is what we are going to prove. Well, at the moment and that P bar is a fractional ideal, right. So, otherwise we have we have not constructed an inverse if P bar is not a fractional ideal. Okay. So, what you do is you so let Y be in P bar, then Y times P is contained in R, right. That is the definition of being in P bar. Hence, Y times P is an ideal in R. Okay. And now this holds for all Y in P bar. Therefore, P bar P, first of all it is contained in, so first of all it is contained in R. is and also an ideal, is an ideal. Okay. But now you notice that R is contained in P bar, right. Remember, so recall that this is equal to set of all x in K such that x times P is contained in R, and of course that holds for every element of R, right. So, R is contained in P bar. This means that P is contained in P bar P, right, and we already proved earlier that P bar P is contained in R. Right. Now, as P is a non-zero prime ideal, P is a maximal ideal. That is the definition of being a Dedekind domain, right. Okay. So, there are two cases. So, hence P bar P is equal to P, or let me write it like this, is equal to R, or P bar P is equal to P, right. These are the only two possible cases. So, in the first case we are done, right. Then P bar is inverse. Well, I still need to say something about being fractional ideal, but I will say that quickly later on. So, is inverse of P, okay. All right. So, I will say that quickly later, as I said. Now, I want to get a contradiction if P bar P is equal to P, we want to get a contradiction. And if you have seen proof of Nakayama's lemma before, then this is very similar to that. Okay. So, we will reduce it to a situation that looks very much like Nakayama's lemma, and then we will use the same idea that goes into the proof of Nakayama's lemma. Okay. All right. So, how do we do this? All right. So, I have taken a y inside, I have taken a, no, right, y is in, okay. Okay, let me quickly say that y p bar is a fractional ideal. So, let x be in P, then x p bar is contained in R and is an ideal. Okay. So, this is minus 0 if you like. Hence, hence P bar is a fractional ideal. Right? This is what we proved about fractional ideals. So, something is a fractional ideal if there exists a non-zero element in case in R such that x times that that set is contained in R. Right? So, all right. So, as I had promised, I said quickly why P bar is a fractional ideal. Anyway, so I work with this x. So, keep working with this x. So, you take the ideal generated by x and it is contained inside P, right. So, there exists P1 up to Pm such that the product of these ideals, such that Pi's are non-zero prime ideals, and their product is contained in X and this is contained in P, right. So, my claim is that at least one of them is a prime ideal contained in P. So, my claim is that Pi is contained in P for some I. So, if not, if Pi is not contained in P for all I, that is the negation of that statement, then take yi which is in Pi, but not in P. I can do that for all i's now, for all i's. Then I take y1 up to ym, this is contained in the ideal generated by x, which is contained in the ideal generated by P, and that contradicts. So, this contradicts that P is a prime ideal. Sorry, I do not need to put brackets around this, that P is a prime ideal. Okay. So, this proves the claim. So, I can assume with by after renumbering, if necessary, assume that P1 is contained in P, but they are both non-zero prime ideals. Hence, P1 is equal to P, right. Okay. So, we have proven this now. All right. So, yeah, maybe what I should have said here is choose minimal such M. So, I can always do that. Okay. Okay. What this means is that P2 up to Pm is not contained in the ideal generated by x, right. So, there exists z in P2 up to Pm, but not in x, right. So, I can take because this is not a subset of the ideal generated by x, I can always take this this element. Okay. Now, I know that z times p, which is simply P1 as I have proven. So, this is simply z times P1, this is contained in x, right. So, although z is not contained in x, z times P1 is contained in x. Okay. So, this means that z by x times p is contained in R, right. So, this means that z by x is contained in p bar. Okay. So, this means that z by x times p is contained in p bar p, which is equal to p, right. That is what our assumption was, that this is equal to p. Okay. Now, we are in a Nakayama lemma kind of situation, where an element times p is contained in p, and we want to get a contradiction from this, right. So, z by the way, I should also say that this is contained in p bar, but not in x, right, because if this were contained in R, then z would be in the ideal generated by R. So, what we have done now is we have constructed an element which is not in R, but when I multiply every element of P with it, I get an element of P itself. Now, this does not look right, and indeed it is not. So, what do I do? So, let A1 up to An be generators of the ideal P. Okay. So, what I get is z by x times A I, This is again in P. So, I can write it as summation B I j a j, j going from 1 to n. Okay. And then I can write down the matrix B to be the matrix of B I j's. Okay. Now, what do? I just take determinant. So, I just take the characteristic polynomial of B. So, what do I need to do that for that? Well, I just need to take t times identity minus B, right. So, this determinant, this is a monic polynomial, is a monic polynomial in R T, right. And what happens is if I put, instead of t, if I put z by x, then I get 0. Right. So, hence z by x is integral over R, which means that z by x is in R. This is a contradiction, because we constructed z by x to be not in R, right. We constructed it so that it is not in R, we constructed it this way. Okay. All right. So, hence P bar P is not equal to P, right, and so P bar is P inverse. So, we have proved P bar P is equal to R. Okay. So, we denote from now on, we denote P bar equal to, or maybe a better way of writing this would be P inverse as P bar. Okay. So, that is how we denote it from now on, because it is the inverse, right. Okay. So, what we have done is we have proved that every non-zero prime ideal in a Dedekind domain has an inverse. We are still yet to prove that every non-zero fractional ideal of R has an inverse. So, this is what we are going to do next time, and as a corollary we will obtain that every non-zero ideal of R is a product of prime ideals in a unique way. Okay. And following that we will prove that ring of integers in a number field is a Dedekind domain. Okay. So, we will get all these results that we have proven for general Dedekind domains will apply to rings of integers of number fields. All right.